The talk starting with an introduction and background, which will be, can everybody hear me by the way? Is everybody okay with the translation and the speed? I'm trying to go slowly. So if anybody would like, I can slow down or whatever. Is it, are you getting the translation or otherwise? Smile, hand up if you can, if everything's okay with the way the sound's going so far. You're good? It's good. Thank you very much. And by the way, if anyone would like to interrupt me during the presentation, I'd be more than happy to answer a question, or we can leave it to the end. So I'm very flexible, and we can do this in a kind of casual way. All right, so as I said, I'll start the talk with an introduction to basic ideas in semiconductor nanostructures that you'll need to understand the material I'll present. I'll then go into two aspects of the optical response of these quantum dots. I'll go into the absorption behavior and the emission behavior by application to two areas where these kind of materials are used, in infrared detection, with obvious applications, and also in lasers you know about, but I'll actually take a little bit of a track into quantum information processing, which is a very hot current topic in this area. Okay, so let me begin. So I'll start from the very beginning, and I apologize for those who've seen this stuff, but I thought it'd be very sad if there were concepts like this that you guys didn't know, and I go through my talk and afterwards you say I didn't understand a word. So I'm going to bore you for a little bit, hopefully, and then you'll all be on track. So the basic idea, of course, with semiconductors is that they are crystalline solids that repeat, essentially infinitely, except, of course, when we talk about these little nanostructures, they do have a finite extent, but we're still talking about thousands of atoms. So they're basically like infinite crystals. So what can we take home when we think about how such objects should behave? Well, firstly, we start with the basic idea of just two atoms. And each atom has a set of states, quantum states. And the first principle, of course, of quantum mechanics is sort of conservation. The states of the individual atoms are not going to be destroyed when we form a crystal. They're just going to get kind of reorganized. Okay? So if you take two atoms together, the states of those two atoms will remain in the collective of the many-atom crystal. And here, when I talk about the many-atom crystal, the semiconductor crystal, as a crystal, it possesses a property, which is symmetry. And the central idea of symmetry is that there's a lattice, that there's a repetition over a lattice constant. There are certain rules which, if this, for example, it depends, it's OH, if we rotate, if it's TD symmetry, whatever the symmetry, the idea of a symmetry operation is that the system will come back on itself through that operation. And in this particular case, the operation is translational invariance. So if I translate my axis from this point to this point by A, if the A is that separation, I could take this point to a similar point over here, and the whole system is invariant, doesn't change. Okay? From that comes a very important theorem, which is Bloch's theorem. So Bloch said that in a system such as this, the electrons, oops, sorry, I'm kind of having trouble here, aren't I? There's the pointer. Oopsie daisy, I'm not having a good time, am I? Okay, oops. There we go. So in a system such as this, the electrons that are solutions to Schrödinger's equation in this system here look like free waves, right, which would be the waves in vacuum, except modified by the lattice potential. So you have a function which will be e to the ikr, which will be a plane wave, multiplied by a cell periodic function, which will describe the new electron in the system. Okay? The other thing that happens is that the states of the individual system can't be the same. And why is that? Because of Paul's exclusion principle. No two electrons can have the same set of quantum numbers. They can't be in the same place at the same time, and so forth. So what happens is that the individual states from an atom will get broadened out into bands, ever so slightly perturbed, if you like, by the crystal potential, and you end up with bands. So that's, if you like, this picture, the real space picture. But if you go back to the picture of the Bloch waves, the waves that propagate and, if you like, get kicked along through the crystal, the other thing is those waves are moving. And so in the moving picture, we use a k-space representation here. If I had a free wave, I would have an envelope function like this here, which is that the energy goes as k squared. Right? So it's just like a kinetic energy argument. If you put into Schrödinger's equation the potential in the crystal equals 0, I'd end up with solutions E equals h bar squared k squared upon 2m. And that would be the parabola which would describe that the electron's motion, or the energy of the electron as a function of its wave vector. In the crystal, we end up with these gaps. These are band gaps, and they end up happening when the electron's wavelength is the same size, or half wavelength actually, is the same size as the spacing between the crystal planes. It's like Bragg's law, basically. So aside from when the electron's wavelength is very short, just like the lattice planes, otherwise the electrons look like free waves. All right, so that's kind of basically it. The other thing is that the electron states at the top of a band and at the bottom of a band have different symmetries. And you can see it kind of over here, and this is at a case at the center of the Brillouin zone, as that's called. You'd have those states. All right, there's a little bit of detail. We probably don't need that amount of detail. What we do need is this first picture I described to you. So let's just recap what that was. That was saying that in an interacting crystal, the individual states of the atoms are not lost. They're put into the crystal state, and because of Paula's exclusion, they get spread. And we have bands with band gaps, openings between them, which open because of diffraction. Okay, those are the ideas that we've presented so far. What else do we need to know to finish the picture off is how many electrons do I have? These are available states. Oopsie daisy. These little pictures here with bands, as the energy goes up, are available states electrons can occupy. But of course, there's only so many electrons in the crystal. So if I took this thing, would say 1 electron per atom in this and 1 electron per this, there'd only be 2 electrons in the system. So I will fill all the way up till I've actually filled to the last electron. Okay? In a semiconductor, which is the things I'm looking at, a semiconductor crystal, we end up that you have even numbers of electrons that end up filling up the last band, let's say it was this one here, right to the top, and there's a gap to the next available states. And it's called a band gap. And the difference between a semiconductor and a metal would be that the band would be half filled for a metal. And the difference between a semiconductor and an insulator is that in a semiconductor, this energy difference that you have to bridge to get to another available state is quite small compared to room temperature KT, whereas in an insulator it's huge, and you're never going to get electrons in these extended states, which are the conducting states. All right, 0 Kelvin, no energy around. So when I start the process filling, and I end with this story here, I have no conduction because the states are filled right to the top, there's nothing above my head to conduct in, and these are all empty. When I have a finite temperature, there's a finite probability of an electron having the band gap's worth of energy, hops across, leaves a hole behind. The hole can move around in this band, the electron can move around in this band. And as the temperature rises, we boil off more electrons, we get more current in the material and so forth. All right, that's all you need to know about semiconductors pretty well. Okay, so I apologize for those that know it, for those that don't, hopefully you've learned something. Something else, actually. I lied, didn't I? Isn't that funny? All right, so what else do I want to tell you? I want to tell you what a nanostructure is. And, you know, people talk about nano everything, but actually the meaning here of nano is that the scale of the object in one of its dimensions is on the scale of the de Broglie wavelength of the electrons. Why? Because if it is, then the electrons confined within their de Broglie wavelength become quantized. And the solutions are no longer extended states, like I described in the previous picture with block waves. Electrons are no longer free to move through the crystal. They're standing waves. They're like the diffraction condition I showed you on the previous slide. They're stuck. They don't move. Right? So if I look at the picture, which says two-dimensional over here, what does that mean? It means that in the thin dimension, which is the order of the electron's wavelength, the electrons can only have quantized states, standing wave states, and they stand. They don't move. But in the other directions in this plane, I'm trying to move this thing, I'm not having much success. There we go, that way and that way. In that sheet, there's no constraints. The electrons behave exactly like the electrons in the previous slide. Okay? So we call this a two-dimensional nanostructure, 2D structure. Why is it 2D? Because there's 2 dimensions where the electrons are free to do what they like, 1 dimension where they don't. And of course, that's called a quantum well, because the electrons feel like they're in a well in that one direction, quantized. In this case, the one-dimensional case, which we'll call a nanowire or quantum wire, we would have 2 dimensions, these 2 dimensions here, where the electrons form standing waves, and only one free direction. So it's only one dimension that's free, 1D structure. And of course, the thing I'm going to talk about today is a quantum dot, where all 3 dimensions are quantized. there's no transport, there's no movement of electrons. The states the electrons occupy are standing wave states. Okay, that's the first point. Hopefully you got that. Next point is that the previous slide, I showed you a picture, and it has pictures like these pictures here, where you've got bands. Well, the question is, of course, how many states are available? If I excite an electron in this first cartoon, this cartoon in the middle here, I put a bit of temperature in, I boil this electron off, okay, it's going to occupy the lowest energy state. There's only one electron, it'll take the lowest energy state. But what about if I boil a lot of electrons off? And you can see there's all these states here. How many available states are there per incremental delta E of energy above that edge? That's the question. And the question is, of course, a simple one in semiconductor physics. You can do that by looking in that case-based picture. And you'll find that in 3 dimensions, if I integrate the available states, you'll see that as I increase the energy from one of those band edges, sorry, I hope you can hear me, sorry about that, from one of the band edges, the states will increase with about the square root of the energy difference from the band edge. As I get from the case of 3 dimensions, no dimensions of confinement, all the way through to 2D, to 1D, oh, sorry, thank you very much, to 0D, what you see is that the states, remember, are conserved. And the state spectrum, the number of states I can find, this is like the number of states I'll find in an increment of energy, starts to collapse down and concentrate. So the time I get to a quantum dot, which is the one at the bottom here, that's that fellow over here, the states are atomic, they're delta functions. Okay? I can only have states at particular energies. And what are the particular energies? Well, it's an atom. Okay? The energies are defined by the quantum numbers, just like in the real atom, N, M, and L. There's also spin degeneracy, but there are 3 degrees of freedom, so we don't count that in our kind of concept of degrees of freedom. So 3 degrees of freedom, there should be 3 quantum numbers. If I looked at the case of the nanowire, the quantum wire, I should have 2 degrees of freedom. 2 degrees of freedom, that means I can sort of think about these two here, which means I should have 2 quantum numbers to define it, right? And so forth with the quantum world, I'd only have 1 quantum number to define the onset states here, where these heaviside functions occur. Okay? So we have states available in the quantum dot, which are the same states as the atoms they came from, but they've all condensed down into a series of these lines. And that, believe it or not, is why this thing is the engine behind all sorts of things like quantum dot lasers you see in this laser pointer, whatever, in communication systems and everything. They all work because of this. So I'm going to try and explain to you why that is shortly. But that's the basic principle. All right, the other principle is, of course, why do you care about the state spectrum? Well, you care because at the end of the day, this cartoon, I put electrons here and holes here. Yeah? How did I know how many there were? Well, I knew how many because I basically took the density of states. This is called the density of states. I took the density of states function, multiplied it by the probability that each state, so let's say I go up here in energy to this point over here. Right? And that happens to be over here on this line. I go here and I see there's that many states available at this energy, but I have to multiply it by the probability that those states are occupied. That's called the Fermi function. So if I'd integrate from the band edge all the way up to where the last electron fills, I'd actually get the number of electrons in the system, which is what I said over here, number of occupied states or the number of electrons. So that's how I would use that information. All right, and you notice I'm trying, yeah, question.
The second plot.
Yes?
It's clear that we have steps. The second plot from
yeah.
But why is this, we don't have a raising.
Yeah, so why is it in the first one we have a smooth distribution, and why is the second one got this?
Yeah, it's clear that steps, but why don't we have raising of the function?
Why don't we have why doesn't the function keep on going up? It does.
Yeah, why these are flat steps?
Oh, why are the steps flat? Right. Okay, so in the way you kind of do the derivation of the density of states, it's a very good question, is you essentially have to, you're taking of n of e dE kind of thing to do that, and you're taking a derivative. So you're taking shells. It's not really very clear here how that was done. So in 3D, you're looking at a differential volume in k-space. So if the states, imagine this thing here describes, let me go back one figure and explain it more clearly. So here, let's say, sorry, I'm having trouble with this machine, right? Let's say this is the band and it's parabolic. So if I take a particular energy, E here, and I cut this parabola, the parabola looks like a circle, right? And if I have an isotropic K, then the circle revolves around and it becomes a sphere. Okay? So, oops, I have a hard time, aren't I? All right. So there's a sphere. So if we look at this sphere, and I'm asking how many states are available, what I do is I say, but in this sphere, which is at K, or E, at energy E, and I look at now adding E plus delta E. I go from that line over here at E, and I go E plus delta E. I draw another circle. And between the two circles are enclosed states in K space. And I integrate those out. So I've got, in this particular case, 4/3 pi r cubed is the volume of the cube. The shell thickness would be 4 pi k squared dk, which would equal the number of states in that interval. But the thing is that energy is still going as a parabola, which is h bar squared k squared upon 2m. So that's why when you take the derivative of that thing to get to when you integrate back, that's why this thing is square. But now if I go in this case, which is the second case, then I'm going to have a circle, not a sphere, right? And the area of the circle is pi r squared. So the first derivative of that, which is the shell, is now going as r. Right? So when I do r by r squared, now I'm ending up with a constant. So it's just the maths, actually. So I can show you afterwards, but that's basically a derivation. All right, sorry if that's not clearer, but otherwise I can get a piece of paper and show you it on the piece of paper. All right, so that's the idea of the states. And the other thing is, of course, I didn't say that maybe clearly. So this is a constant, pi h bar squared upon 4, right, is the constant there. So each step brings an equal number of states as we add it. But the other thing is, of course, this number here, this would be like E0, which would be, for this case you asked me about the quantum well, E0 would be the ground state of the quantum well, which is the first allowed state. And although it's not clear from here, I mean, could anyone tell me, since I like to do an interactive thing, so do you think that this energy here should be the same as that energy there?
Yes.
Okay, no is the answer. That's good. I like that. I know, I'm kidding. I like to do that. I'd be naughty. Oh, it's not. Who can tell me why? So, what do you think the principle? Who can remember an infinite quantum well? You'll give me the answer. That'll make it easy for you. You can give me the answer. So, an infinite quantum well. What happens in an infinite quantum well? Yeah, the states. The first allowed state is an S function, right? It's like a sort of half a bow, and its energy goes. Let's put as proportional to 1 upon L squared, right? So the narrower the well is, the states move up from the bottom of the well. But if you've got states in there, you know they're not at the bottom of the well, because the self-energy, the fact that the electrons are forced to be in that space with themselves, essentially, raises their energy. So what happens here, that's why I was going to try and see if anyone caught that, is this energy here, which is the energy, the first state in that potential well, is not equal to the same state as if it was unconfined. And that would be like your E0. This would be your first excited state, E1, second excited state. So just in case you were kind of thinking what that all meant, hopefully I explained it to you. Sorry I picked on you, didn't mean to. All right, so how do we make, so we understand hopefully a little bit, and please ask me more questions and hopefully I'll try and get clearer as we go, so I won't be completely as, whatever, crazy. So let's go to how do we implement these nanostructures, right? Okay, we've hypothesized, wouldn't it be lovely to have a quantum dot or a quantum well or whatever? How do we make them practically? How we do it is this. We make, and these are called heterostructures. So I'm going to explain now how these structures are realized in practice. And we start by the idea of materials with two band gaps. This is material A, which could be, for example, aluminium arsenide. It's a typical semiconductor you can grow that turned out to be lattice matched to gallium arsenide. I'll tell you why that's important in a minute. Here's gallium arsenide, something probably people have heard of for a long time, and here's aluminium arsenide. So imagine I take the material with the wide band gap, we've just spoken about band gap, and I interpose the material with the narrow band gap between these two pieces. I end up with that. Sorry, I'm pointing, looking, that. I end up with a region where if you think about the potential for electrons, it's going down here. So the lowest energy for electrons is lowest in this material in the middle. And the lowest energy for holes is lowest because the scale reverses for holes, right? Is lowest here. So I have electrons and holes both want to collect, if you like, in this material in the middle. And it's a heterostructure because it's a structure between two materials, different materials, which form this structure. And it's actually our quantum well, right? It's the same thing I kind of spoke about before, except if I did it in 3D, it would be a quantum dot, right? So here's a picture, actually. We grow these things too, we make these structures too, but I thought I'd be nice and pick someone else's. So I don't know, my evil nature came in or something, who knows. But what you can see is you can see that these structures are perfect structures, right? When they're made in practice, the atoms line up, you're looking at single crystals of one material and single crystals of another material, and you really, really do make a structure that's composed of the two materials, and it's quite beautiful. And as a result of this thing, because if the length here, this width is like half a wavelength, half the electron wavelength, I'll end up with electron states confined in the quantum well per what we just discussed earlier. So we can have discrete energy levels just like in atoms. We can control the number of electrons in this system and holes. We can control it, as you'll see in a minute, by any number of means. And depending on the size of this thing, because remember I said to you, imagine the infinite potential well. Well, you know that it goes as 1 upon L squared. So if I make a narrow potential well, the levels become further separated, widely separated, and a wide potential well, and the levels look almost like bulk-like. So quantum dots refer to as artificial atoms where we, in 3D, are going to make structures like this. All right, so that we've kind of got, and the sort of things you want to think about are interface quality, the materials that you can do this with, impurities, because you want to try and make this thing perfect. All right, so this is getting there. The last slide of silly stuff that, a couple more actually, I just realized, but anyway, almost the end of this painful session for you guys, before I actually talk about some stuff, is optical response. Right? Because the talk I want to give you today is about understanding the behavior of materials. Last time it was all about transport, about the movement of charges through materials, semiconductors. Today it's about light, how light interacts with these materials and how we can build useful devices and structures from them. All right, so very simple ideas here. I don't want to kind of complicate things. So we've got the two bands. This could be the quantum well or whatever. It doesn't really change the argument. We've got incident light comes in, and the light has a frequency which is, or an energy, higher than the band gap, which means that it can take an electron from an occupied state down here to an unoccupied state above here. That's called absorption. Simple as that. So when you say you've got absorber, it's just doing exactly that. And of course we care how many states there are and everything else, but that's fine. But what does it generate? It generates, this process of absorption generates a pair, an electron and a hole. Okay? If those are correlated, we'll talk about that later, those are called excitons. But let's leave them alone for the moment and assume they can walk through the crystal and they could create a current, and we'd call that a photodetector, a photodiode, right? On the other side, I've put in some light, I've generated the pair, and now, as I said earlier, the lowest energy for the electron in this system here wouldn't be up here, because we know the minimum energy is down here for these electrons in this band. So they're going to relax down, they're going to lose some energy, relax down, and finally you'll have an electron and a hole here. That electron and hole can recombine to essentially repair the crystal. So we'll fill the open state here, and we'll empty out this filled state up here, which is how the crystal was, if you like, at 0 Kelvin, if you imagine. And we've put the crystal back down to equilibrium. That process, that latter process, will emit a photon of energy equal to the band gap. Okay? So that, if you like, if I hadn't done it with light, you might call that a laser, like the thing I'm using right now. Right? In a laser, I use current, drive current, to drive electrons and holes into the system in a particular region. They recombine, that's what this process is called, and emit light. And this is the light you're looking at. Okay? So those are the two very basic ideas you need to know about how to make, about emission and emitters, lasers for example, and absorption and detectors. Okay? All right, so we have a small statement over here which I'm going to elaborate on, which is, actually I don't need to go over there, do I? Which is about good emitters and bad emitters, but we'll get to that in a second. Before I do that, I'm going to use the formalism of boring stuff that I told you earlier and see if any of you are still awake at this point. It's going to go on, it's going to be bad, right? All right, so what I'm doing here is formalizing in the simplest possible way I could the two ideas of absorption and emission. And the way it works is this. Imagine the band, the lower band, which is the valence band as it's called in the semiconductor, which is generally occupied, and the upper band, which we call the conduction band, which is generally empty, is going to be called respectively E1 and E2. Okay, those are our two states. I've reduced the problem. Being a physicist, you always reduce problems to the most stupid way, and I try to make it as stupid as possible, and that's good. All right, so we have, in the absorption case, we have our initial state now, where the electrons were sitting, and the final state where the electrons ended up, right, as being separated by the band gap, and our light was coming in, h bar omega, that's the energy of the photon that came in, and it's taken us from the filled state to the empty state. The absorption coefficient, the thing that measures how good that process is proportional to a few things. It's proportional to this thing called JDOS, joint density of states. That is the density of states argument that you asked me a question on and so forth from the previous slides. How many states are there available in the initial band? It's proportional to that. And how many states are available in the final, right? Because you have to have both things available. You need the states available for you started and the states where you end. Sorry. That's the first factor. The second thing is you need to know whether those states were filled or empty. And in this particular example, of course, the initial states have to be filled, so there's an electron there in the first place, and the final state has to be empty, so the electron can occupy that state once it gets up there, right? So that's the argument. And that's for a normal population. That is that if I go back a few slides, the normal population being this thing's filled, that thing's empty, or even at room temperature, that's mostly filled, mostly empty, right? That's what we call normal. If, on the other hand, we go with the case where, just like the previous slide, I'd been irradiating, let's say, my semiconductor with light, or I'd been passing a current, like in this laser diode, to fill states. Well, then I keep on filling the upper states, and at some point, I'd have more electrons up here than I would down here, right? Which means the upper state is basically filled, and the lower state is basically empty, right? So in that particular case, we're going to have an emission-dominated example. And to look at the emission probability, which is just like the absorption one, again, it goes with the joint density of states, and now the probability is not that E1, which is the lower state, is filled, it's that the lower state is empty. It's available for the down transition, right? And that the upper one is filled. Okay, and that's called a population inversion because it's inverted, that we assume that this thing is full of electrons when in the normal case it would be normally empty. So it's inverted from its normal condition. Okay, is everybody okay with these ideas? So far so good. All right. So let's put together something called Beer's law, which you all know about. Everyone knows about Beer's law, is the idea of attenuation. If I have a solid and I have a light beam, I'm trying to think, I've got no hands here, right? I can't put something, point anything. If I had, I had my laser pointer and it went like this, it's light, boom. Okay, light comes on the surface, it's got an intensity, it's a photon flux, hits the surface. The minute it moves into the medium, it gets attenuated in the normal idea of Beer's law by an exponential amount. The deeper it goes, the intensity drops off exponentially. Fine. But if we want to include absorption and emission, we can see that obviously this is a reverse process. We can put the emission coefficient in here like this. And why does that help me? Because it now helps me define this object in the middle, which is our semiconductor quantum dot, for example, as a sort of optical media with particular characteristics. And let me describe what I mean by that. I'll talk about three cases. Think about the case when alpha exceeds E, when E exceeds alpha, and when they're both equal. Those are the three conditions we want to look at in this example. So when alpha is bigger than E, let's say much bigger, then basically this term here is positive, and the thing in front is of course negative, which means that the intensity is going to go down by minus this constant Z, right? So it means, just like in this condition that I just described, we diminish the intensity on the output. So when I look at the dot, the left of the dot, and I look at the right of the dot, I would call that dot an absorber. Okay? If I go to the other condition, which is that E is much greater than alpha, then you can see because E has got a negative sign in front of it, then the coefficient of this whole thing becomes plus EZ. So the intensity grows. That's a laser, right? So we have something which is actually gaining. As we move through the medium, the electromagnetic wave gains energy. It gets amplified, effectively, as it moves through, right? And that's the example I showed here. So if I look at the incident wave and I look at the wave coming out the back, amazing. It's a bigger wave, so to speak, on the output. That's the idea of gain. And lasers work on gain, okay? The middle condition is alpha equals E, which of course means that the coefficient is 0, e to the 0 is 1, so I equals I naught. The material is transparent. Okay? It's like there's no quantum dots in there. Okay? That's the middle condition. And we call that a transparency or threshold condition for a laser. That's kind of the terminology. All right, let me put it all together in these slides over here. So imagine the absorption. This is essentially alpha, if you like, absorption. So in a normal material, normal population condition, then with increasing energy, I start at the band gap because I need a minimum photon energy of the band gap to bridge the band gap. So at the band gap, this thing increases. Who'd like to tell me what they think the shape of this curve is? Roughly. You're going to get it right. I'm telling you. My friend in the front row is going to get it right. It's like a leaf. It's like a what?
Leaf.
Leaf?
Tree leaf.
Tree leaf, yeah. But it's about root E. That's what you said. And that's the right answer. Sorry, I'm having fun. Why is it like root E? Because the density states. Do you remember we had joint density states? Joint density states. Both density states went with root E in 3D, which is what I had here, right? So that's why this thing would look like that. And if it were a perfect gain media on the other side, that means the population was totally inverted. So this band would be filled forever to the top, and this would be empty. Then I would have the same shape on the back side. But because alpha and E can both have values, I end up with a profile which can go when I push enough photons in and I upset the population to invert it sufficiently. Once I've pushed hard enough, I can get a curve to go into the gain region here, where there's more electrons up here, if you like. There's a bunch of electrons up here, and there's a bunch of holes down here. And that's called the gain region, and that's what a semiconductor laser does. If I flip the curve around, and I just look at the gain side here, you'll see that we have a region of wavelengths where there's gain, where the semiconductor can show gain. And the way you make a laser, and that can be done by injection, you can put the carriers in, and how a laser works is we put mirrors on the end of this block of material, and those mirrors make the light bounce back and forth just like in a quantum well. We spoke about quantum well states. This is the optical equivalent. It's called a Fabry-Perot. So the allowed states for the light in the cavity are also quantized, and they're called modes. Those are the loud oscillations, right? The longer the cavity, the tighter those modes will be. The shorter the cavity, the wider the spacing. Just the same argument as the quantum well I gave you earlier, right? So it's no different from a quantum well. It's just an optical quantum well. So the laser light you get in this pointer comes from putting it can only laser in allowed modes. It means you multiply this thing by that thing, which is what that is, and that's what a lasering spectrum is. And the more I pump, the more I change occupation, the more I'll select one of these modes till I finally have a single mode laser like this thing. Okay, that's how a laser works, and that's kind of the basic idea. All right, I think I've given you all the theory. Yes, I've given you all the boring theory, so hopefully now we can use that theory in the last part of the talk to understand things, and that's what I'm going to do. All right, so the first thing I want to tell you is we need to make perfect structures, right? Why do we need to make perfect structures? Because if I end up with the electrons I inject in the system being wasted at interfaces, not recombining through band to band, they're useless. So for the kind of devices we talk about, the state of the art in making stuff is actually molecular beam epitaxy. There's also MOCVD, but for the kind of things we look at, MBE, as it's called, is better. MBE is a very simple idea. All the stuff so far is simple, right? So what is the simple idea? It's that obviously I want to nucleate this stuff, and I want to nucleate it perfectly. So I need a bit of temperature so that the atoms that impinge on a surface can find their sites and can organize themselves appropriately. That's very important. How do I actually implement that in practice? Well, first of all, I want only the atoms I want. So it has to be a very clean system. I don't want extraneous atoms because dopants and things really ruin everything for me. So what I do is I take little holders, which are called Newton cells, which will emit a beam of atoms by their geometry and the ideal gas law, and I won't go into that now, but it's a kind of very clever little idea about how this works. But it's basically a little furnace where I put ultra high purity elements of whatever I need in these boxes. And what are the elements? Well, if I were telling you about aluminium arsenide and gallium arsenide in that previous thing, I'd need aluminium, gallium, arsenic at least, and maybe some dopants if I'm going to put some dopants in later, right? But what I do here that's special is I put shutters on this thing. So what I can do is I can turn on and off those elements. So if I want to grow the gallium arsenide, the aluminium arsenide, like I showed you in the picture previously, I grow aluminium arsenide. Then I shutter off the aluminium source, turn on the gallium, and I'll have gallium and arsenic together on at that point in time. I've grown my gallium arsenide, etc. So you have very, very tight control, pure elements, it's very lovely. But how do I ensure the thing's clean, and how do I maintain the fact that the atom from here gets to here in a predetermined way? And the way I do that is by having ultra-high vacuum in the system. So if I clean this system out to the level of 10 to the minus 10, 10 to the minus 11 torr, typical of our system, you end up with the mean free path of an atom from one of these Newton cells being of the length of tens of meters. So we have no problem getting an atom from here to here, and also the time it takes for a monolayer of extraneous material, things we don't want, to form on the surface is so long that we don't worry about contamination. Right? So I can grow ultra pure, ultra fine structures. In fact, because the growth rate we work with, everybody works with, is so slow, typically a monolayer per second or even less, it means that I can control things to monolayer precision. Okay? So you know the size of the structure. If I just go back to that picture, for example, right? You're looking at the atoms. You can see how many monolayers. Remember, there's two atoms in there'll be two layers in a monolayer of gallium arsenide, let's say, right? So you can see that we're looking at really very few, tens of monolayers. That's what we're talking about here, tiny structures, right? With high precision, perfect interfaces. That's kind of the basic idea. All right, so what else do we have to know about? Well, we're trying to grow these materials, put these materials on each other, and we have to realize whether they're compatible or they're not compatible. Gallium arsenide, that I showed you earlier, has gallium arsenide and aluminium arsenide lying above each other in lattice constant. Band gaps are different, but the lattice constant's the same. So there's no problem with strain. The two materials have the same lattice structure. They're both zinc blende, which is a form of face-centered cubic lattice. So the atoms can line up perfectly with each other. And the only thing is that if you like the probability of a particular site on your zinc blende lattice being, say, gallium or aluminium, in this case, would be in proportion to how we do it. And the band gap would change, in proportion. If I look at a system such as the one in the blue here, which is a solid solution, that means I have gallium arsenide and indium arsenide. Those materials certainly don't have the same lattice constant. The lattice constant difference here is 7.4%. They're hugely mismatched. Right? So even though I can get the narrow gap material to have a very nice narrow gap and the wide gap material in my heterostructure idea wide, look at this difference here. This is a problem, you say. In fact, people have studied the idea of strain building up cumulatively as the thickness of an epilayer would rise, trying to accommodate, if you like, the difference in lattice constant by deforming one lattice, the one obviously you put the epilayer on top from the one below. And what you see, and this is kind of like a Matthews-Blakesley theory as they call it, you see that depending on the system, and this is indium arsenide, as I move along here adding more indium, all the way to finally go over here, you find that with more indium, there's more strain, so the thickness, the critical thickness before this thing dislocates and forms and doesn't really basically work for me at all, and I'll tell you what I mean by that in a second, is rapidly diminishing. And the time I get to indium arsenide on gallium arsenide, I can grow on average 1.6 monolayers. If you look by STM, scanning tunneling microscopy, you'd see about 1.6 monolayers. Not really working for you. So let me just tell you a few things about those ideas in a second. But before I do that, just make sure you understand some of these ideas. So the idea is just shown in these cartoons below. Again, imagine this is the gallium arsenide substrate. Here's my indium arsenide layer I want to put on top, or one of the materials along this continuous solid solution. If I have a thin amount of the material on top, I can strain the material, change its lattice constant from what it would be as an isolated material, which is this picture. And in this particular case, this is called a biaxial kind of deformation, right? I stretch the lattice in one direction, but keep it going in the other. But at some point, when the thickness is sufficiently large, I no longer have coherent planes that follow through from the substrate to the epilayer. I actually end up with defects at its interface, and those are dislocations and things which can carry charge and kill me. And finally, if the mismatch is too large, of course, the strain is relieved completely, but I have a material which is useless because it's all dislocations at the interface, right? So that's the basic idea. All right, so yeah, I don't think I have to say that's said here, and it's talking about how that biaxial compression works. So let me talk a bit about how this works from a kind of thermodynamic perspective, which I think is probably interesting for you guys. there are different growth modes that can occur based on the free energy. The free energy, the net free energy change that we'd be interested in, will be a free energy for film, free energy for the interface, and free energy for the substrate. And if you imagine growing, and the green stuff is supposed to be growing on top of the substrate. So if the free energy is less than 0, and it doesn't change with increasing amount of material deposited, I'll go down the left line here, and this is called the Frank-van der Merwe growth mode. Basically, it's stable all the way for layer-by-layer growth. If I go the other route, which is the route on the right-hand side of this diagram, the free energy is greater than 0, which means it's not favored for thin film growth, so to speak, from the very beginning, and islands grow. That's not actually like that, but islands would be all the way from the beginning. That's called the Vollmer-Weber growth mode. No wetting, as I said, no layer-by-layer growth, islands all the way. In the middle, you have the growth mode I'm going to talk about, which is called the Shrantzig-Krasnikov mode. I probably said that very poorly, but anyway, I tried hard. And the idea is that you can have the 1.6 monolayer average wetting layer, but once you've gone below a certain thickness above, the strain is built up and growth breaks down and we island. Okay, so that means you've got island growth plus you've got island growth on top of a wetting layer. And that's basically how quantum dots look when we grow them by MBE. And if you wanted to understand why that would be, this whole dependence on size, there's also this idea about two aspects to the quantum dots themselves. There's a surface energy difference with their size, and there's a volume energy. So when we look at the total energy, you can see that the volume energy term is going to play its role kind of over here, the surface energy term at the top, and it's going to be a critical thickness which will be stable, above which thin growth is stable. So island growth will occur once you kind of get beyond this critical thickness, when the free energy is kind of going down. All right, enough of that. Here's some pictures, which will make you happy again. All right, so we've got the example of the islanded growth. You see a wetting layer, which is supposed to be the thin gray stuff, and you see the indium arsenide islands on top, and here's a picture of how they may look. STM kind of pictures. This is a TEM picture of one of ours, of how these growths look, and they can be surrounded completely by the gallium arsenide. So there's your three-dimensional nanostructure we were speaking about. So in my group, we can do that. We have MBE. We have lithography, so we can kind of put contacts on this thing and make a laser. We can also check how it behaves. And I kind of showed you that last time. So I'm going to talk about some of the techniques now. Oh, this is actually what MBE looks like. So how do you make it? You make it in a system that looks like a sort of some kitchen utensil or something. Basically here, schematically, would be your Newton cells, which are the thing at the bottom. Substrate, which is sitting on this pedestal thing, which rotates, would be basically coming down from the middle here. And to get it in there at UHV conditions means basically transferring it in through all these load logs. All right. And here are some pictures of these kind of nanostructures. So of course we can grow all sorts of stuff in that kind of approach. We can use catalysts and actually grow nanowires, even with dots in. But I'm going to focus on dots. And there are self-assembled dots, and there are also dots that can be patterned dots. And I'm going to talk a little bit about epitaxially patterned dots for things like quantum memories, and information processing and lasing and so forth. So we'll get to that in a second. All right, so to remind you now, let's say we've been able to grow these quantum dot arrays. Here they are, lots of nice quantum dots, and we want to actually think about using these things. So what we're thinking about now, and I'm going to refine the model now and tell you that the ground state in a quantum well, of course, has got allowed states, and the excited state, so to speak, if it's absorption, also has some allowed states. So there's two types of absorption we can consider. We can think about the ground state as coming from the valence band states that we've described to this point, and this would be called interband because it's between valence band quantized states and conduction band quantized states. Or we could do between states of one band, and that's called intraband. Okay, intraband. So we're going between E0 and E1, let's say, in that conduction band. Okay, there's two different ways, and they can be used for different things. So let me give you examples of stuff we've done, where we'll start first with interband absorption and why it's kind of very interesting for different things. So my first example is the idea of a quantum dot saturable absorber mirror, passive mode locking. What's that about? That's about basically having a device which cleverly controls how to chop light up into pulses. Okay? How does it work? Works as follows. I have some light coming into this device, and I have this red layer, which is that layer of quantum dots. It could be many layers of quantum dots, which is going to be my absorber layer. And then I have behind it, I have this thing, which looks like a kind of bunch of dielectric, actually, and it is exactly that. It's like a mirror. Now, how does it work? Well, you know, with glasses or whatever, how they make dielectric mirrors, you basically take two dielectrics with good contrast, and you alternate them. And what it does is it essentially retards the wave and also rotates essentially the wave vector around. So if you imagine without this red line in here, light would come in and essentially rotate round and come back out. Okay? So what's the function of the red layer? It's actually kind of written through here. So we have high power incident light, which is the left, this top arrow, comes in and is absorbed by the red quantum dot layer. It takes electrons from the valence band ground state to, subband states, from, make sure I got that, from these states up to these states. What that does is it means that while those electrons have been taken upstairs over here, they're filling these upper states, and we've suddenly got population inversion. Remember I described that earlier, population inversion. Upper states got more electrons than the lower state. So what does that tell me about absorption at that point? No more absorption, right? There's no more states at the bottom available with electrons to be raised up. So once I get to population inversion, the material becomes transparent. So remember I said when alpha equals E kind of idea, material looks transparent. So once I've absorbed this and created carriers temporarily upstairs, the light pulse is going to go through. Before, the light pulse was stopped. Now it goes through. Turns around, and it's coming back here. So what happens next? All right. What happens next is during the round trip time, the electrons up here have gone through to so-called trap states, which exist in these systems. Trap states very quickly take the electrons and very quickly drain the electrons back down to ground. So there's a quick, easy way of taking electrons out of the system. And it happens quickly, and you can see the time scale here. So while the pulse has been doing it dithering around, the pulse, the time it gets back, will suddenly see an open gate, right? So you've got an automatic chopping of the light by this ultra-fast process, picosecond process. So basically, you can use that to mode lock a laser and to tune and control the temporal behavior. And that's something which is used now today very frequently. And we kind of developed that. And here's kind of an example of that from some work we did. Okay, so the actual practical, this is kind of how people use it nowadays. And you can see the actual device consisted, for that work, consisted of multiple layers to actually get the absorption, a decent amount of absorption for the high power laser. And the Bragg mirror looked exactly like in that picture. And everything was fiber coupled, so you had something which was incredibly compact, ultra fast, chirped system. All right, let's go to the next idea. Let me just flip back a few while you're still half awake. All right, the other idea I was going to tell you about in absorption, which remember is from lower state to upper state, while you're thinking to yourself, why am I here? This idea, I wanted to talk about intra-band absorption with quantum dots. All right. So before I do that, a bit more theory, get you really glazed over. I want to talk about an application to mid-infrared quantum dot photodetectors. So there's many, many applications people are interested in nowadays for that. Things like, for example, people doing atmospheric studies where they're trying to look at pollutants in the atmosphere. Things like astronomy people are doing in the infrared, mid-infrared. Things like medical work. People are doing quite a bit of mammography and so forth. Ton of work. People want to look at and have detectors for the mid-infrared. Quite difficult. So what basically goes with the absorption? I gave you a kind of a very simple argument. The more elaborate argument is basically that there's a coupling that couples the two states. We call that the matrix element. And then, of course, there's this occupancy factors, which are the probability of occupation I gave you earlier. And that basically tells you a few things. That there's a few factors we're concerned with our quantum dots. One is their size. The size will tell you how the states and their occupation are determined. The second thing is the number of dots. So if I have a low dot density, I have few absorbers to absorb the light. So what I'd like, if you think about these equations here, is I'd like to have a high areal density of absorbers, and I'd like to have them all the same size, so that at the same energies that I'm going to dial in, they'll absorb. Otherwise, there's going to have absorption from one dot at one energy where the quantum states are further apart, and another one at a different wavelength because these states are closer together, right? Because the size and the wavelength, of course, go together, from what we said earlier. So how might you go about making efficient infrared absorbers? You can, for example, try and control the size by things like templating. You can use lithography. This is called KOH etching. People do quite normally, quite regularly, to form little pits that are determined by the crystal structure. In this case, they're 1-on-1 planes. In semiconductors tend to be dense planes, slow etching, so you can kind of do that. And then you can use epitaxy, which basically follows those crystal planes, leaving you at the pits with, in fact, a quantum dot. Trouble is, of course, you get dots and wires, and more importantly, because the size of the thing at the top is so big, the density, the number of these dots you're going to get is going to be pretty low. So then you may be able to control size, but you certainly can't control density. And I'm just kind of showing you here, these are the self-assembled dots that we spoke about by Stransky Krasnikov, our stuff. You know, you can make layers of them and stuff, but you can see they're all over the map in size and so forth. And also the density is not great. So what we've done is we've looked at nanoscale templates, basically sort of like a colander or something like something where there's little holes, and you imagine you use those holes and you only let the growth occur in the regions where there are holes. In that case, you could, oops, jumped ahead there. In that case, you can control the size of the dots because the dots are only going to grow where the template has an opening. You can control the shape of the dot, which means how the wave functions look, which means the probability amplitudes. You can control the density, certainly, because if I make the template small enough, or the spacing between where the holes are small enough, I'll get a very high density in there. And I can also do other things with these, which I'll talk about later, which is that I can make lattices where the electrons on each dot can communicate with each other, which are things like excitonic lattices and God knows what, which are particularly interesting nowadays as topics. But we'll leave that alone for now. So let's stick with the first ideas. How do I make these dense things? I can do it based on some work that Matsuda and Fukuda in Japan came up with. Everybody's known how to make anodic aluminium for many, many years. It's been known since pretty well the industrial age. But making anodic aluminium, which has ordered pores, is different. And that was basically Matsuda and Fukuda who showed how you could find the conditions, they found the conditions, for growing structures that have pores that look like this. Those can be used as templates, which I can stick on top of a substrate. This is done in alumina. We did it in alumina. And here's a gallium arsenide substrate beneath. Van der Waals bonded. And you can see you've been taken a section, so you're looking through the pores just like in this picture here. And you can see these pores go right through to the substrate here. We've opened the pores up with phosphoric acid. And so you can see that I can grow with the MBE system, let atoms come and they'll go down these tubes, and they'll only grow at the bottom of the tubes. So I can make arrays of quantum dots in principle with such an idea. Well, how much controllability can I have? That's shown in this diagram. So by changing the anodization voltage, I can adjust, and also changing the electrolyte I use from sulfuric to oxalate or phosphoric acid, I can adjust the pore dimensions from anywhere like 10 nanometers in size, tiny, tiny holes, all the way up to hundreds of nanometers. And of course the pore density would go appropriately because the structure is a hexagonal kind of close-packed structure. And here's a picture showing you how these things might look. You can make them tall, you can make them thin, you can make them fat and wide, do what you like with them. And of course, there's going to be an issue about getting material down the pores, which means is why we were looking at various thicknesses and so forth. Net result, one last concept is that with the pores, we can do the MBE experiment like I showed you before, gallium atoms, arsenic atoms. Oh dear, that didn't look good. You're going to be let off the hook soon. What does this mean? I'm not sure. It's in Russian. Okay. Maybe good. Power's ending? Oh, should I plug it in? It's not my machine, but... It's okay, or should I be doing something with it? Just leave it, right? Okay. All right. Let me know if I should be doing something, because I can't read the Russian on that thing. All right. So the idea is that, you know how I said before, if you make a superlattice, or a quantum well, I said that you go from gallium arsenide, you turn on the aluminium, then you turn off the aluminium. Okay, you can do the same thing here. I can grow a layer of, say, gallium arsenide, grow aluminium arsenide, gallium arsenide, but now it's not in a thin film. It's in a dot, right? So what I've made is I can make dots that are homogeneous, right? These are dot lattices. Kind of pretty, right? I like these things, I'm so happy. These are the quantum dots, as they're called. And you can see they're very close to each other. They form a hexagonal lattice, right? I can control their size and whatever. That's one idea. Or I can get really clever. Not clever, but I can get really ambitious. And here I've put 2 quantum dots inside of the quantum dot. I put 2 quantum wells, actually, in the quantum dot. So I have disks of confinement here and here, because there's gallium arsenide in between aluminium arsenide twice in the dot, right? And that's what each of these dots are. So you can make very complex heterostructures in that way. I'll come back to why that's kind of interesting in a little bit. But actually you'll see pretty well now. All right, so we also have been working with General Electric, actually. They're trying to make infrared detectors for looking at all sorts of things. So what we wanted to do, whoopsie daisy, that's my next pretty picture coming up. You shouldn't see pretty pictures too often. They also developed a process different from ours, which is called block copolymer lithography, which essentially was to develop extremely fine patterns. This says 20 nanometers. We actually got patterns down to 2 nanometers. You can make incredibly tiny dots. So with an incredibly tiny dot, of course, band gaps are huge, right? The level spacings are huge, but really tunable, right? So that's kind of the ultimate way to go. And what do we achieve with that? I'll just kind of explain. These are now inter-subband absorbers. So the principles I told you before, going between those subband states in the conduction band, can tune it. So this is the first excited state kind of transition, and it's massive, it's huge, it's bigger than band-to-band absorption that I showed you in the previous thing in terms of its effective responsivity. Right? That means response to light, the signal. We built these photodiodes, which are basically so-called pin structures of the big field, and when the absorption occurs, we can extract the carriers out easily, and we can detect with great precision photons. And that's why we made a camera, basically, with those arrays, which you're looking at someone's ear. Maybe mine, actually. I'm not sure whose ear that is, but it's got a lot of heat coming out of it. Okay? So, you can look at black body radiation and so forth, and you can filter it, and you could look at anything you like. So that's the idea of using those principles in different ways. So we spoke about 2 states, whether they lie within the band or between the bands. But it's the same idea, and it's very simple. It's more about technology. How do I implement that thing? And that's kind of what I just tried to show you. Okay, so any questions on that? Yeah. Or I can move on to the next. Yeah.
You cannot get resolution files half of infrared wavelengths. What's the point to put 2 nanometer quantum dots with such density if it's still have the differential limit?
Okay, so let's go through kind of the size. It's intra-band that we're using here. So what we're trying to do is the transitions are between allowed states of the quantum dot, so that it's not actually, let me make sure you understand. Here, it's this cartoon. So we're actually doing these little things. So what we're tuning is we're tuning the subbands, so that when the size gets very small, that's the only conditions when you're going to actually have ability. If you kind of go through the dielectric constant of gallium arsenide, that's the only point where you'll actually be able to move those levels around. Otherwise, you'll have no response whatsoever. You'll be controlled by shot noise, which is basically thermal noise. So you need to be able to separate those things reproducibly so that those 2 states can be apart. The other question you mentioned, the other point, which is a very good point, about why the density. The density is because of the responsivity. So there's 2 things you see in the figure. Here. You see that not just that the bandwidth here is fairly narrow, which a normal infrared detector would have actually a square root would be like goes up and square root down sawtooth, which is kind of what you're getting at. Very narrow. This is relatively spectrally narrow. And it's spectrally narrow because all the dots are roughly speaking the same size. It's high for these. If you look at the dot density, the number of dots and whatever, the actual responsivity, which is essentially the measure of that, is high because there's so many dots there. And a large fraction of them, I won't say all of them, are actually absorbing. There can be non-radiated recombination, which means that some of them, which are seeing light, are not actually producing a photocurrent. But basically, a large fraction of them, that's how you can tell. So that's roughly speaking. Hopefully that helps you. Yeah. All right. If there are other questions, I'll kind of keep moving. So let's talk about emitters. Oh, it's done again. Should I be doing this? I hope I should be doing this. Or is there something more fundamental I should do here? Oh, thank you. Yeah. Should I leave this alone, or should I be... Oh, it's the plug that's not working. Oh, thank you. I don't know if over there maybe, right? You know what? Yeah. That's a great idea. Thank you very much. Good. Appreciate that. Yeah, maybe move it slightly like that. Yeah, that's good. Oh, not long enough. Yeah, I don't know what to do here. Yeah, I think it's okay. Beautiful. Thank you so much. Appreciate that. Okay. Microsoft. That's a universal problem, right? Microsoft. Okay, so I have to go back a bit, don't I? All right, so the next kind of, I grouped, as I said, the talk into pieces, right? Basic introductory theory, so hopefully you got a bit of the idea of the principles. Absorbers and now emitters. And the diagram of the whole talk was basically two levels. One's going up, one's coming down. And we're at the end, so we're going down, right? Everything's going downhill from here. All right, so stop my jokes. Quantum dots as emitters, which means looking at these basically inverted systems. I apologize, it's a bit busy this slide, but let me just briefly point a few points out to you. So we said the emission rate going from the upper... Oopsie. That's weird. That was the end of the talk. That was pretty good, huh? Getting to the end of the talk that quickly. No, I don't think it was. All right. From the upper state to the lower state, we said goes with the joint density states and the probabilities of occupation. So if you look at the band here, and we assume that we've got an occupied state up here to one down here, and the bands are described by this parabolic band, then we can use the relationship in the joint density states to express that joint density states, as I told you, is the root E, as well as the probability functions. Assuming simple non-degenerate statistics for occupational Boltzmann factors, you should end up with the emission distribution intensity looking like your joint density states and the probability factors, that is the empty state beneath, filled state above, giving you this factor looking like a spectrum like this. So if I said, what's the spectrum of emitted light from a laser in terms of the population argument, which is this, I'd expect to see something which peaks not at the band gap, right, which is what I've told you all along, which is why I kind of did this, not at the difference between these two here, or not at the difference between here and here, but slightly higher, because you've kind of sampled the population or weighted the population by where the carriers actually are, where the available states are, and so forth. So that gives you something which, roughly speaking, has a narrowish half width, goes up to about 1.85 kT above, or 1.8 kT wide, if you like. That's what I expect. And I'd expect that if I took a laser, shone it at a semiconductor, and sometime later turned off the laser light and had a look at the emission, I'd expect to see a spectrum like that. That's called photoluminescence. All right, so I like this one. I don't know where I took it from, but it's kind of funny. Anyway, so the idea is what I just said just now. If I want to know something about what's going on with these states, I can pump it. I can push light at the system, and I can watch the light that comes back, just like I said it. That's called photoluminescence. Like the lady here, and give her a bit of a prod with the mouse, and she starts to sing. All right, so we're trying to see the singing crystal. So in my lab, we have a ultra-fast spectroscopy system, and that's kind of what you have to do the experiment I just said. because you're pumping it, you're giving it a kick, and you want to see quite a short time later, because those carriers are not hanging around. The carriers that you've created are mobile, right? Or they move around. Even in a quantum dot, they kind of are moving in some sense in their states. So you need to have fast systems to understand what's happening and understand that energy relaxation process. So this is a titanium, oopsie daisy, this is driving you crazy. Titanium sapphire laser. That's just a silly way of saying a tunable laser that offers pulses down to the level of femtosecond. So roughly the order of 100 femtosecond we run it at. All right, so, and we also do something a little bit fancier than that, is that we're interested in particular dots, right? So I've got a quantum dot, like this kind of fancy array of dots, or I've a particular feature. I want to know what that particular quantum dot is doing, right? Because the gentleman asked me a very good question about the behavior of a system of dots and so forth, and I said, well, some of them work, some don't. And he didn't ask me the obvious question is, well, which ones? But actually we could tell him, right? So he probably thought I was joking when I just said that, if he'd asked the question. But we can go around and we can literally resolve down to single dot spectroscopies. And we can do it with a confocal, nonlinear confocal setup, and we also do it in a near field scanning optical microscope, an NSOM as it's called. And we do it at low temperature, obviously, because we want to remove the thermal noise in the system. It's very, very important. All right. So the system kind of looks a bit like a mess of stuff, but as I said, it may look messy, but there's nothing really to it. So, you know, it kind of looks impressive, but it's more like kit than anything else. So you've got your Ti sapphire. You can't even see over here the pump laser. So there's a nice pump laser, 532, 10-watt pump. It pumps the Ti sapphire. You've got an OPO amplifier there. You've got an SHG, second harmonic generator. Pulses come out. You can tune them whatever wavelength you want. So it can be resonant pumping or non-resonant. And then it goes through a mess of optics, which is basically your microscope. We'll call it that. And then it comes through this Mitutoyo objective and everything else, pinhole, etc., right, to the cryostat, where the sample sits on a nanomover stage. We can move this thing around with nanometer precision to find our dots, single dot, and then we can collect the light back out through the same system, dot, dot, dot. We can either look spectrally in this system here with the liquid nitrogen called CCD, or we can look over here in this Hamamatsu streak camera with picosecond resolution as to how that system is changing with time for that particular atom, that particular quantum atom, whatever you want to call it, quantum dot. All right, that's roughly the story. So that's the tool. You need a kind of funny old tool, and there's more rubbish here, but I think that's enough rubbish. Okay, so you don't need to see all that kind of crazy pictures. So we've got a lovely hammer, which is our laser system, to investigate these things. What do we expect to see? I mean, it's all very well having kit, but it's actually useless unless you actually know what it is you're looking for and why. So again, I'm going to drive you insane, but I'm going to tell you a basic idea, which is that, you know, you pump the system up. Here we go, pump, light goes in, I give it the laser for excitation, and I'm this optimist, which is going to be channel over here with PR on it, the optimist channel, which says that everything I put in there comes back out as light. Remember, that's the story I've given you so far. Well, I have to tell you I was a liar. Excuse me, that's very bad, but there you go. All right. Not exactly true. Some of the light, some of the carriers can hit back down to ground through another channel. It's called non-radiative. It means that it gets back down to ground, but it doesn't involve the emission of light. And in fact, I already told you the story, so you knew. I'm not quite a liar, because when I told you about the saturative absorber mirror, I said to you that the way it relaxed was through these intermediate states, and there was no light. So you've already heard the story. So I'm kind of a partial liar. All right. So here we go. The quantum efficiency, basically then, of this process, which is very important for emitters, is the ratio of how much of the energy goes through the radiative channel compared to how much goes through all channels, radiative and non-radiative channels. Okay? And if I had a trap in the middle of the gap, and I know there's some excellent work being done here, people looking at trapping in semiconductors and deep levels and so forth, you'd see that basically the probability of that non-radiative transition would go with an activation, an Arrhenius factor, depending on where that trap energy sits, if you like. That's the delta E trap upon KT. So if you put the non-radiative term into here and you solve that thing, you'll end up with a quenching term, which should look as 1 plus some constant, the Arrhenius factor, right? 1 upon that. All right, well, there's a few other things you should know about some of the radiative part. So the radiative part is also occurring, or non-radiative, but let's go radiative, is occurring in the absence of the laser light to some degree too. What do I mean by that? Well, I mean that if I have a material at thermal equilibrium, nothing else around it, at a particular temperature, it's in equilibrium with the surroundings. We call that a bath temperature. So if you like, the phonons, which are excited from the black body radiation that the solid sits in, they cause a certain population of generation events here and recombination events. And of course, the higher the temperature, the more we're going to have these two things. And by detailed balance, those two should be equal, right? So if you think about it, you can take either one of these two here, but basically, when I have a generation event, let's call that a generation event, I create N0 carries up here, and P0 carries 0, referring to equilibrium. So the rate is then proportional to the population of these two. Every time I have this event, I have one of each, so it's proportional to the product of those two. And there's a constant in front, which is a constant, if you like, of this equation. And then, question? Oh. So, what was that? It's for me? No? No, okay, sorry. I don't understand that, so sorry. Thank you. So if I shine light, what happens is the population now is higher than equilibrium. It's not N0, but it's N0 plus delta N0, right? Or delta N, excuse me. And P is not P0, but P0 plus delta P. So I can write a similar equation because the probability is also still of a recombination event, let's go the reverse here, right, is still proportional. In order to have a recombination, I have to have a whole electron and a hole for this thing to happen. Same thing, I have to have an electron and a hole, except the populations have gone up by the injection, as I've explained, from light. So different semiconductors behave differently in this regard. Obviously, the first thing is, if the band gap is direct, which means that the conduction band edge lies above the valence band edge and no phonons are involved, or indirect, when I need to bridge this gap in this difference, but the minimum energy for electrons is actually at a different K. It means I need phonons and electrons, right, in order to get a recombination event to occur. So the probability of having A and B, of course, is much less than just A. So the B, which is essentially what we're talking about here, for an indirect gap semiconductor, which would be the bunch at the top, should be much smaller because it's much less likely than for direct. And if I look here, you see 10 to the minus 14 or 15 for these chaps at the top. If I look at the direct gap ones, 10 minus 10, 10 minus 11. So what have I got? 4 or 5 orders of magnitude difference in the chance of getting light out of an indirect gap semiconductor compared to direct. So if I want to take silicon and make a laser, what's the answer? Don't bother, right? And that's why no one's done it. You don't make semiconductor lasers from these materials. And people have tried doing all sorts of kind of clever stuff, but you're really fighting nature, okay? All right, the other thing, of course, is that that coefficient B would depend on temperature too. And that basically because of the occupation factor argument. And also just the softening of the bonds. So as the temperature rises, if you like, the springs which hold the atoms together weaken. So the overlap between of the potential between adjacent sites reduces, so the band gap will reduce. All right, so let's just do a few quick things on what else can happen if I inject too hard. If I try and pump the semiconductor too hard with light, I have my laser intensity going on is really, really hard. Then I create lots and lots of electrons. Oopsie daisy, I'm really driving everybody mad, but I apologize. Lots and lots of electrons here. So I have a new opportunity in these kind of materials. That is that the electrons are now going to have very high energies, and the holes can have very high energies too. Which means that the electrons with high energy will have high momentum. So they're moving fast. They can bash into each other to slow down. And in fact, when they do, then they cool down effectively in this system, and then the probability of a recombination event, of course, goes up. So we have then a three-body process as the next most likely thing, which means 2 electrons in this case, and then a recombination with a hole. And that's called an Auger process, and it's going to be proportional to an electron and an electron, that's the first and second, and that electron finding the hole to recombine with. So that's a three-body process, and it's only likely when you've got lots of electrons around, as you can see it goes to n squared, let's say here in this particular case, or you've got a material which is heavily doped intentionally with lots of carriers in it, which could be also a small band gap material. Right? And the different Auger processes, it could be an EHH process, which means 2 holes recombining with an electron, whatever. But they're non-radiative generally, or very inefficient type of processes, three-body process. The last one I want to bring you to attention is the fact that quantum dots, which we're kind of back to the beginning of the story. What are we doing here? Sure. Quantum dots have surface, and surface is not bulk. That is, in the bulk of regular semiconductors, you have atoms with atoms above them, atoms below them, which means you don't have bonds like these, which are unsaturated, carry charge. So what that does, that charge, is that's a means for recombination. It's a mechanism for dissipating energy. But also, the thing about surfaces is that they're not ideal. That's an ideal surface. It means it's basically a mirror of the structure in the bulk. But real surfaces are not those. Because the minute I take the constraint of the atoms on the top, what happens? Well, what happens is there's no forces on the atoms on the top, right? So they change their positions. And that's called relaxation. And in fact, if they change their position sufficiently because of the self-interactions of those charges here, they actually can reconstruct, which means I eject atoms from the surface. So the density of atoms on the surface can also reduce. So the picture of charges on the surface is not the picture of charges in the bulk. And generally speaking, it's a place where there are fields, because there's charges, if you like, a charge symmetry creates a field, and it creates places where recombination is rife. All right, so with that, you have a picture that essentially the same story I told you about traps is really that these are not states of the crystal. Remember the block states that we started the whole story off with this morning? Oh, a long time ago. They're not block states. They're not states of the mixed atoms. These are states which are states of the surface, and therefore they belong in the band gap. Just like trap states are states which don't repeat in every unit cell of the structure. So we end up with states that lie in the band gap, and their occupation, just like traps, will determine the recombination. And you can have trap-assisted capture and recombination, and the basic story of that is that the rate, which is 1 upon tau, 1 upon the time it takes to recombine, will go with how many traps you've got, which means the areal density of these nasty things. We'll go with the capture cross-section, which is essentially where the local field is that's dragging something in. And we'll go with the activation energy, which basically means the work required, or the how deep the trap is, if you like, with respect to its ionized state. All right, so that kind of came back to the trap idea, and that gives you all the radiative recombination things you need to look at. Oh no, it's not. There's more. There's more and terrible things. So I won't go into that. I'm just going to label and name them and not tell you about them. So we just really talked about what happens with the up and down. There's also excitons, and that's the last thing. These are called free-to-bound transitions, free-to-bound with donors and acceptors, and even deep-level transitions. They don't really do a lot for us as far as we're concerned, but this one with the excitons does, and I'll just finish the story off with my little exciton story about fried eggs. All right. So the thing is that when you create the electron-hole pair, right, when you do this excitation in the semiconductor, you create an electron and a hole, those two things can actually be attracted together and move as a unit. They don't have to be independent, okay? And they can move through the crystal, and they'll have a binding energy. And you can treat this thing, which is an excitation of the lattice, as something called an exciton, and you can treat it as the hydrogen atom problem, basically with the dielectric constant of the crystal in there, and an effective mass, which would be a sort of effective mass which would take in both the electron and hole, if you like, center of mass kind of problem. And if you do that, you kind of come up with a binding energy for these excitons, which is pretty small, which means that, you know, depending on the material, either they're going to be around at room temperature only in certain materials, or often not. And to see these little fellas, you have to go to lower temperatures so they don't dissociate. The ground state of the exciton in this example would be n equals 1, and we would call any states above that excited states. You can of course get even biexcitons if you pump the system large enough, which are these condensates, which would be excitons flying around together. Good. All right, so let's see what we got from arrays of PL. We actually got the spectrum. These are these little quantum dot arrays, depending where we had dots and wires in them. Simple, it followed this beautiful spectrum we expected for the simple bound-to-bound, simple exciton emission. So we seem to know what we're doing with that. We could even do the same thing with different materials. So this was actually looking at quantum dots, gallium arsenide base, Al-gas. There it is. These are Al-gas gas structures. You can use the same technology, which you couldn't use because it's Strancy-Kresnikov, to do the same thing for InGas. And again, everything works out beautifully. And the other thing is, of course, you can now use these to control how light behaves itself. How's that? Well, just a quick thing on polarization. So the light you've got, you can now start to organize it because of the asymmetry of the wave functions. If I have a monochromatic wave here, plane wave, coming on my material, you can think of this wave basically described in terms of these components, field components. So you can say that, and it's traveling in the z direction, so in the xy, the field is going to lie in the xy plane, and we'd have these two field components for x and y. And we could write out, with x and y being periodic functions of this kz minus omega t, we'll write out this equation, which basically is the equation of ellipse for the way the polarization of light is going to sit. And basically we have a polarization for the light which can be expressed in terms of either being linearly polarized in this form or circularly polarized. So I can go ahead and you can calculate, you can do band structure calculation of these dots, and from theory we should be able to get extremely anisotropic. You can see very high emission here, polarized emission, something like 80–90% is exactly what we got. So not only we can see the dots, but we can also see the way the carriers and their wave functions in their confined structures are actually settling. So what you can do with such structures is you can engineer not just the size and scope, but exactly where those electrons sit and how they sit as we inject electrons into it. All right, so just to finish this little section, who cares about this in terms of emitters? Well, people really do. Because if I look with time, the history of lasers, you'll see that, you see like Eophi and people like that here, right? It's kind of fun. You'll see that lasers have basically gone the way of what I told you are nanostructures, these semiconductor nanostructures. They started with the quantum wells. That's called double heterostructure, sandwich, right? Then they went into quantum well, quantum wire, quantum dot. And that's where we are now, and that's what we're talking about. And why do they do that? And because if I look at, say, a quantum well, this is, you know, you asked me about density of states. So here's your density of state spectrum for the quantum well. The Fermi function, which is the occupation, comes in like this. And you can see that there's not much room to play, so to speak, with absorption compared to if it were 3D. But if I get to 1D or 0D, basically the Fermi function occupies this thing or it doesn't. And everything is recombining in our language through these quantized states. There's no room to play. So if I change the temperature, right, the Fermi function can broaden, but basically it's still going to emit on those states. So it's completely temperature insensitive, which is an incredibly important thing for communication systems and so forth in terms of these lasers. The modulation bandwidth is tiny. It is extremely high because the tiny volume of the dots means that you can basically empty them, so to speak, from an electronic point of view, extremely fast. You fill them up with carriers, you empty them really quickly. Spectral line width is incredibly narrow because you're dealing with this distribution we spoke about. And by playing with the quantum dot dimensions and the number of dots, you can really play with the amount of gain you get. Okay? So that's roughly what I wanted to say over in this slide. All right, so the last little bit of stuff is really moving towards quantum information and putting things together, which means the ideas of trying to manipulate bits of information in complicated quantum structures. So we've kind of worked in a few areas. One of the areas was, you need to have controlled structure. So here's the idea we originally were kind of looking at, which is that we said, you know, you can take something like a ramp, essentially, where diffusion is very fast on this ramp. Atoms move up and down beautifully. But here they don't move so fast. So if this is indium arsenide growth, the indium arsenide atoms roll up the top and they then nucleate on this ledge. And basically by restraining the size of the ledge, because of the strain argument and diffusion arguments, we can end up with linear arrays of quantum dots, which we can build into optical cavities. And we can kind of control their sizes, we can control the emission intensity in these different channels and so forth. So let's talk a bit about trying to control information. Let's actually talk about entangling information. And in order to get you to entangled information, which is like sort of where things are going, the future of basically using information with these systems, let's talk about the exton, that fried egg I showed you earlier. So with the exton, basically you have, I just give you the principle so you can deduce what I wrote up here. You have S-like quantum dot conduction band and you have P-like valence band states. So if you go through the symmetry of, say, the P-like states, the 3/2 states, which are sitting down below for holes, the heavy holes, and you've got the spin half states up the top for the electrons, given what I just said at the top here. These are the four possible types of spin state we could imagine for this exton system. You could have the -12 for the upper state, you could have the 3/2 for the lower state, minus, etc., and the plus and minus. These are all the four possibilities. So if you look at the transition rule between states, because of parity, right, because of the delta n and delta m symmetry rule, then only these two are allowed. These two here, of the other two available, will not be allowed. They won't satisfy that rule, which means they'll be dark states. Okay? So what does it tell me? What should I do in order to look at these two states? So if I took and this goes back to the polarization thing I told you earlier. If I took a right circularly polarized photon coming at this in the z direction, which means down onto the quantum dot, which is beneath me, it can only create the +1 state. Why? Because what it does is it's stimulating the transition from the heavy hole, the 3/2, -3/2 state, to the -1/2 state. That's what it says over here. And how can you figure, why do I call that +1? Well, because the removal of the electron, which has angular momentum +1/2, right, which is, you know, going to, in this case, is going to be the -1/2, so minus becomes a plus, will correspond to the creation of a heavy hole with the opposite, with the minus state of angular momentum. So we end up with basically 3/2 minus the -3/2, if you like, or minus -1/2, which is equal to the +1. And the same thing if you want to take left circularly polarized light. So if we look at a diagram here, which explains what I try to say in a strange way, if we take our quantum dot in its ground state and we use right circularly polarized light, we'll be able to put it into the +1 state. Left circularly polarized right into the -1 state. We can continue, actually, this story up to not just one exton, but two extons stuck together called the bi-exton, which is sitting at the top. And so what that tells me is that I basically have, and here's the energy structure of this thing. Okay, here's the left and right circularly polarized, etc. The ground state system with one exton in it, in the two spin states, and the bi-exton state at the top, noting that the bi-exton state is more stable than the two single exton states. If I double the energy of the two exton state, I'm up here, but this delta lower is the bi-exton, which is what I wrote over here, right? All right, so what does this all say to me? And secondly, of course, with my little dots, which I can control the size of so beautifully, I can then control the energy of the exton energy and the bi-exton energy. So I can control this level structure, where it exists, how I can access it. Okay? All right, so what we've got here, why do we care? What am I trying to say? What I'm trying to say is that if I've got bi-extons in this thing, the bi-extons can decay down by emitting essentially this route and that route, emitting two photons, right? So you've got two photons which are stuck together. The thing is that the two routes kind of work either one route or the other route. So the polarization of the first photon will determine the polarization of the second photon, coupled together. But since these two channels are indistinguishable, it's like a beam splitter, right? So those are entangled states. And here is, if you like, the format of this entangled state, referring to the polarization and the state being, you know, a bi-exciton state or a single exciton state here. So we have two paths which are entangled because their paths are indistinguishable. And with that, if you do things right, the meaning of why this is interesting is because you can generate, if you like, these prepared entangled photons for quantum computing at very, very high efficiency, with high fidelity. Okay? Normally, it's been to this point in time before we kind of came up with this funny idea, which I'll tell you about. It had been 80% at best. Most people were sitting around 50%, which means that really it wasn't sufficient to do quantum computing. We kind of came up with a scheme that was not 100%, but in the 90s, which is a huge, huge change. And how does it work? Okay, so there's two ways of doing it. And the answer is that, first of all, how do you populate the quantum dot system? You populate it either optically, which is how I've been talking about things all the way through to this point, or through electrical injection. Electrical injection is like the laser I'm using. Optically is by the laser I showed you on the bench, which looked awfully complicated, but was frankly nothing more than a source of light. And you know, we're talking here, this is kind of some of our work on that. You can see the exciton and the bi-exciton states, and you can actually spectrally resolve them from function of size and pumping, which means how we occupy them. So what we kind of, to this point in time, people had been, oopsie, what's happened with this thing? There it is. No, there, yeah. People had, there's been a whole bunch of schemes to try and make basic light-emitting quantum sources. And they want to do it very, very fast. But all of these techniques were basically looking at non-resonant excitation. And the problem is that you statistically populate all of the exciton states, the bi-exciton, the tri-exciton, the single exciton, and you have jitter, which means you're moving between them in time. So it's really not just that it's inefficient, but it's unusable, because frankly, you really have an indeterminate population base. So the answer is, you want to do resonant excitation. You want to actually be able to speak specifically to the energy level structure that's been built by the size, shape, etc. of these quantum dots that I showed you. And the idea here that we kind of were talking about is the idea of resonant excitation using pulses, picosecond pulses. And you can either do two color pulses, which would be this route, or you could do single color, two photons of the same energy or wavelength. I won't kind of bore you with the details of basically how you would calculate those schemes, but let me just give you the result, make it easier, because I think this will probably bore you stiff otherwise. Basic result is that with the two color, if I use a sequence of 1 picosecond pulses, I can get 99.7% population transfer, determinate population transfer. Even using the same pulse, picosecond, coincident picosecond pulses, I'll get 99.1. So you can basically, and single color excitation will give you 95.5. So you can develop a scheme which is basically like photons on demand in a determinate entangled state, which is kind of what I was saying. All right, why is that? Where's that going to go in the future? What's the context of what that might mean? Context is that once you've got these photons, you can start to put them through processing. Very easy. You can start to think about waveguide systems, you can think about modal transfer, you can do frequency transforms on them, you can do a Hadamard gate, you can do whatever you like. So basically it's suddenly amenable into traditional silicon photonic integrated circuit land. And that's kind of where this thing's going. All right, so the last thing is, in order to take a source like this, which is a quantum source, you need to actually increase its cavity dynamics, which means basically narrow its line width. And you do that by putting it into a cavity. And in our case, we've been working on these quantum cavities. So what we're looking at is why do you care about these cavities? Because light matter interactions in photonic cavity, photonic crystal cavity, which is critical to a photon lifetime, enhance certain things. In particular, we care about the overlap of the modes of the crystal with the absorption gain spectrum, essentially, that I talked to you about, of the emitter. And that's called Purcell effect. And it goes with the Q, which is the efficiency of the cavity to hold light, and the modal volume, how tightly you can squeeze that light mode around the emitters you want. In terms of the QED stuff, cavity quantum electrodynamics, the parameter is actually slightly different, but pretty well the same. So what we're trying to do is we tried to make nanowire type laser cavities with extremely high Q. And we did that, and you can just see them here. These are the pictures looking down on these cavities, which you can now embed the dot systems into. And here are the modes that we're looking at. And I'll just go to the cut to the chase. So the Q factor is basically tells you how fine this is, which means how well can I take the light that I put, and how well can I hold it, and therefore use it to process. How many, and what I mean by that is, if I can hold it as long as possible, I can do a billion, trillion, whatever, operations, computational operations in the time my computer needs, right? So essentially the clock rate of my computer is determined by the line width of this thing because of the inverse time, right? So that's what I just wanted to show you that we did, and that's what we're going to put together. All right, so just to end, and I'm sorry I went on for so long, I apologize, it's very boring, but anyway, modern growth in processing technology enables an unprecedented control over making nanostructures. So what I mean by that is, you know, everyone knows you can get monolayer control, but you can not just do that, you can do it in 3 dimensions. And you can organize structures in 3 dimensions. You can put them in cavities in 3 dimensions. And because of that, you have access to really remarkable types of behavior, which in the future probably will come out with really interesting types of things. Careful engineering of such structures enables you to see their unique quantum properties. So traditional things such as satchel absorbers, inter-subband detectors and so forth obviously can be accessed, as well as much more advanced applications, which I ended on, such as the quantum information processing. So thank you very much. I think that was my last one, with some people sitting around, definitely quantum, definitely classical. So I had to try that one. Thank you very much.
Thank you.
And I apologize, I went a little bit too long for you guys. Any questions, or would you guys like to have a break and just take it easy? I'm happy to.
No, I have a question, but
Yeah.
I'm really sure it's...
Hope it was enjoyable to some degree at least for you guys. Yep, question, sure. Oh, that's perfect. I like a question.
For my English,
No, sorry for my Russian.
is there a simple answer? You need a strain in quantum dot nanostructure.
Right. So the question was, why do we need strain? And so what I kind of tried to allude to with when I showed pictures of the templated gallium arsenide, aluminium gallium arsenide dots and indium arsenide ones, prior to our work, people hadn't made anything but strained quantum dots, because the mechanism by which they made the dots was Strantny-Krasnikov growth, which itself is driven by strain. So if you look at indium arsenide quantum dots in that process, they automatically have 2 things going wrong with them. They have strain, which lifts the degeneracy of the heavy hole and light hole bands, and it also, because they're embedded in structure, they end up being intermixed, which changes the composition. So the quantum properties, which determines by both strain and intermixing in the more traditional way. However, that can be useful. So if I'm after polarization anisotropy or something, I might want strain because it can help balance it. If I want to make a traditional laser, people like strain because what I just told you, actually, if I have tensile strain, will shift the effective number of electrons and number of holes in the gain profile contributing to lasing. So normally it's asymmetric, so gain is limited by which population of carriers is in the minority. So by actually playing with strain, people make strain lasers, which actually work very nicely for that reason. However, for some of the applications we were looking at, we don't particularly want strain because there's something called Pickus and Beer, famous actually Russian scientist, was involved in trying to understand so-called deformation potential and what it does. In the structures we're looking at, the strain actually would be a problem because it would change the symmetry and would change some of these selection rules and where these states are. So it depends what you're trying to do. Sometimes it's a plus and sometimes a minus, like Pickus and Beer. Both are a plus, but you can decide. I hope it was a straightforward answer. Thank you. Any other? No?
Can you return a few slides back? There was a graph with energy.
There was a graph with energy. This one?
No,
Oh.
right. This one.
Yeah.
How did you obtain it?
Right. So do you remember that system, that photoluminescence system I explained to you? So photoluminescence, as I said, is just a simple technique where you take bright light, which is above the band gap, you shine it at the semiconductor, creates carriers, and the carriers recombine. In this particular case, we were looking at single quantum dots, and we kind of filtered through, and this is done at very low temperatures, doesn't say actually. This was done at 1.6 Kelvin. So you put in a cryostat, which is pumped. 4.2 Kelvin is helium, you pump the helium, get down to 1.6. Everything about the rest of the setup is what I described to you. So the Mitutoyo objective, we used the usual spectrograph kind of idea, and that's kind of how you measure this thing. So the intensities here, oh sorry, I'm wrong. It's a wrong material. This is the pump intensity we're looking at. So the point where I showed this is the luminescence, right? And the luminescence is collected by the CCD, a liquid nitrogen cooled CCD camera. So those are the two axes, right? The wavelength, basically the spectrometer, the intensity of number of counts from the CCD. The reason for this thing, what I was trying to show, was that at low number of photons, this is microwatts essentially is the flux, microwatts per centimeter squared is telling you the flux of photons that we're exciting with. This was actually 710, not written in there anyway. Wasn't 710? Was it 710? Yeah, it was 710. 710, so I'm just going through my head just to make sure before I tell you the wrong thing. 710 nanometer excitation, so slightly above, slightly higher in energy than these peaks. And obviously this is the flux of photons. As we start to increase the flux of photons, you're populating more and more excited state carriers, and you're going from single excitons to, you now have a probability that they're going to be bi-excitons. That's all I was trying to show, and you kind of see the population initially rising here, and this one being nothing, and then there's a kind of a flip that starts to happen at a critical threshold, where you start to see the onset of bi-exciton emission. Was that roughly what you were asking me, or? Yeah. Okay. Any other questions? Or? You're good?
What's the big on the right? Like,
What's the... This?
No, the right is one more big.
Oh, here?
Yeah.
Yeah. So that actually is... All right, that's a substrate, actually. Yeah. So there's a free carrier, basically polar optical phonon free carrier effect, so which has got nothing at all to do with this stuff, so I'll leave it alone. Yeah. So if not, thank you very much, gentlemen, ladies, everybody. Thank you.